Hello friends, today we discuss about some basic concepts and solid state topic. First of all, we look the basic thought, positive thought. Stay positive, work hard, make it happen. Now we look the objectives of lessons. So dear students, we discuss today the packing efficiency of FCC and the density of crystal. In previous lecture, we discussed about the packing efficiency of SCC, BCC, and now in today's lecture we discuss about the packing efficiency of FCC and the density of crystal systems and solve problem on density. After we look defects in crystal structure, electrical and magnetic property. Defects, already defect means there is a irregular arrangement in the solid, or there is an imperfection present in solid. So best example of imperfection or fault or irregular arrangement is the brass, bronze or stainless steel. These are the day-to-day life examples. After we look the electrical property and the magnetic property of crystal lattice. Now first of all we explain packing efficiency of FCC. FCC means face center cubic unit cell. Now see the structure. See the structural arrangement of FCC. There is AC. See the AC length, it shows 4R. And see the triangle of ABC. According to the Pythagoras theorem, AC is equal to under root AB square plus BC square. If we consider AB as a edge length A and also we consider BC as a edge length A, so equation becomes AC is equal to under root A square plus A square. So AC is equal to A root 2. So now there are two values, AC is equal to 4R also and AC is equal to A root 2 also. So now equate both the values. AC root 2 is equal to 4R. So A is equal to 4R divided by root 2. So now in the next step, see already we know the packing efficiency formula, that is volume occupied by atom into Z divided by total volume of unit cell into 100%. Already we know the formula of the volume occupied by sphere or atom, that is 4 by 3 pi r cube, but the Z, that is number of atoms are present in unit cell, FCC unit cell is 4, so that's why multiplied by 4. So 4 into 4 by 3 pi r cube divided by total volume of unit cell, already we count that 2 root 2 r raised to 3 into 100%, and after the calculation we get the 74% packing efficiency. Okay, after that we look the relationship between radius, edge length of common unit cell system and their packing efficiency. See, there are 3 common unit cell systems. अगर हम देखेंगे तो 3 common unit cell system है that are SCC, face center cubic unit cell, body center cubic unit cell in chart. See, this is face center cubic unit cell and body center cubic unit cell. Now from this chart we can predict the relation between radius, edge length, volume of atom, packing fraction, packing efficiency. First of all we look simultaneously. First of all we look simple cubic unit cell. In that simple cubic unit cell, see the R and A relation. R is equal to A by 2, so the volume of atom 4 by 3 pi the cube of A by 2. Packing fraction, that is pi by 6, is equal to 0.52 and packing efficiency in percentage, that is 52. After we look face center cubic unit cell, see the R is equal to A divided by 2 root 2. So volume of the atom, that is 4 by 3 pi A divided by 2 root 2 raised to 3. Now packing fraction root 2 into pi divided by 6 is equal to 0.74. In percentage, packing efficiency is 74%. In body center cubic unit cell, R is equal to under root 3A divided by 4 So the volume of atom 4 by 3 pi into the cube of under root 3a by 4. The packing fraction, that is under root 3 pi divided by 8, that is 0.68, and the packing efficiency is 68%. Now see the summary chart of SCC, BCC and FCC. Already we know these are the common types of systems. Number of atoms already we discussed, but see in the chart, SCC shows the number of atoms 1, coordination number in 2 dimensional it shows 4 coordination number, and in 3 dimensional it shows 6 coordination number. The arrangement, SCC shows AA type of arrangement, and the packing efficiency, that is 52.4%. Next one, BCC. BCC shows number of atoms 2, coordination number in 3 dimensional, that is 8, no specific kind of arrangement, and the packing efficiency, that is 68%. FCC shows 4 number of atoms, Z is equal to 4, number of atoms are 4, coordination number in 2 dimensional 6, in 3 dimensional 12 coordination number, and in the arrangement point, in the arrangement chart, see there are 2 kind of arrangement. FCC shows 2 kind of arrangement, ABAB type and ABC type of arrangement. In ABAB type, FCC shows HCP kind of arrangement and tetrahedral voids. In ABC type, FCC shows CCP, that is closed cubic packed arrangement with octahedral void, and the packing efficiency in percentage, that is 74%. Now see the density of crystal. See the formula of density, that is Z into M divided by Na into A cube, and the unit gram per centimeter cube. Now see the conversion, picometer into the centimeter. 1 picometer is equal to 10 raised to minus 10 centimeter. This is very important point for the problem solving purpose. This is very important conversion. Now see the problem. Solve problem on density. First of all, see this problem. In this problem, the copper shows 0.1278 nanometer radius, atomic radius, and its mass, the copper shows the mass, that is 63.5 gram per mole, and already we know the Avogadro's number, that is 6.023 into 10 raised to 23. Calculate the density of copper. We know the formula and put the values, and after we get the density, that is 8.933 gram per centimeter cube. In this problem, we find out the density of copper. Now see the next problem. In this problem, we find out the mass of the silver. We have the formula, that is D is equal to Z into M divided by Na into A cube. So we can find out the mass. M is equal to A cube into D divided A cube into D into Na divided by Z. From this formula, we can predict the mass. So put the values in the formula and we get the mass, that is 107.09 gram per mole mass. Now, after we look the packing in voids of ionic solids. There are two types of voids are present in the ionic solids. Already we know there are tetrahedral voids and octahedral voids are present. So tetrahedral void shows 2:1 ratio and the octahedral void shows 1:1 ratio. See the comparison. Do the comparative study. So it's very easy to grasp. See the, for example, Li2O, Na2O, Li2S, etc. And the radius ratio of tetrahedral void is R cation divided by R anion is equal to 0.225. In the octahedral void, already we discussed the ratio is 1:1, and the large cation and large anion shows basically octahedral void. For example, NiO, MnS, NaCl, etc. The radius ratio of octahedral void is R cation divided by R anion is equal to 0.414. After we look radius ratio rule, already we know the radius ratio rule, that is radius ratio rule shows the difference. The radius ratio rule shows the R cation divided by R anion ratio. So following chart gives a relationship between radius ratio and coordination number. See, there are coordination number 3, 4, 6, 8. See the limiting values, types of geometry and examples. Now, first one, see, if the coordination number is 3, then the limiting values are 0.155 to 0.225 and the type of geometry that is trigonal planar. And the example is boron oxide. Next one, if the coordination number is 4, then the limiting values that are ranges from 0.225 to 0.414 and the type of geometry that is tetrahedral and the example is zinc sulfide. If the coordination number is 6, the limiting values that is 0. ranges from 0.414 to 0.732 and the type of geometry that is octahedral and the example is NaCl. And the last one, if the coordination number is 8, then the limiting values greater than 0.732 and the type of geometry that is cubic and the example is cesium chloride. Now, after radius ratio rule, we look the defect in crystals. Alrighty, defect means name itself indicate that defect means fault, irregular arrangement or fault or imperfections present in solids. So see, this is a chart, and from this chart, see the simplification of this classification. Point defects, actually there are two kind of defects, point defect and line defect. Point defect is causes due to irregularity arrangement between atoms, ions, molecules, and the line defect is causes because of irregular arrangement in lines. So that's why now we are interested in point defect. We are going to study only point defect. So see the classification of point defect. Point defects is classified into further 3 types: stoichiometric defect, impurity defect and non-stoichiometric defect. पॉइंट डिफेक्ट ये 3 पार्ट्स में क्लासिफाइड किया है: stoichiometric defect, impurity defect and non-stoichiometric defect. Stoichiometric defect is further divided into 4 parts: vacancy defect, self-interstitial defect, Schottky defect, Frankel defect. Impurity defect is also further divided into 2 parts: substitutional impurity defect, interstitial impurity defect. And next one, non-stoichiometric defect, is further divided into 2 parts: metal deficiency defect and metal excess defect. Now, in the next point, stoichiometric, we'll look the stoichiometric defect. First of all, point defects are classified into main further 3 types. Already we discussed in previous chart: stoichiometric defect, impurity defect, non-stoichiometric defect. Now first, we'll look stoichiometric defect. स्टिचोमेट्रिक डिफेक्ट मतलब उसमें जो डिफेक्ट होता है, जो भी एटम्स और जो भी मॉलिक्यूल्स उसमें इन्वॉल्व होते हैं उनका रेशो फिक्स रहता है. देर आर इन फिक्स प्रपोर्शन. ओके, देर आर इन फिक्स प्रपोर्शन. सो दैट इज कॉल्ड एज स्टिचोमेट्रिक डिफेक्ट. Vacancy name itself indicate that. Vacancy defect means itself indicate that there is create of vacancy, means there is positive or negative ions are missing and they create a vacancy. So there is a decrease in density of that particular substance. Okay, that is naturally if there is a loss of cation or anion ion, there is a decrease in density. Next one, interstitial defect. When some constituent particles and interstitial site, the crystal is said to have interstitial defect. Means there is a positive ion or negative ion. For example, there is a positive ion if leave its original site and situate in interstitial, that means in void spaces, interstitial space, and go into the interstitial space, and that is called as what? Interstitial defect. Now see next one, Frankel defect. Frankel defect, this is also shown by ionic solid. Smaller ion means there is a smaller cation. Smaller cations are present and they are dislocated, means they are leaves their original sites and go into the interstitial sites, means if there is an empty space, they go into the empty space, and it creates the vacancy defect at its original site, and an interstitial defect at new location. Frankel defect is also called as dislocation defect. This is very important point. For example, ZNS AgCl, that means silver chloride, silver bromide, silver iodide due to small size of zinc, Zn2 plus and Ag plus ions. These are the examples. Okay, means Frankel defect mainly occur if the cations are smaller in size. This is important noting. Now, next point, that is Schottky defect. This is vacancy defect actually. Okay. In previous slide, in previous point we look, that is Frankel defect. There is no changes in density. But see, the Schottky defect, basically, this is the vacancy defect. In this defect, there is a missing of equal number of positive and negative ions. There is a missing of very important point. There is a missing of equal number of positive and negative. That means cations and anions are missing, and that's why there is a vacancy created, and Schottky defects decreases the density of substance. This is very important point. Note it. Now the number of such a defect in ionic solid is quite significant. Now see the example, that is NaCl, KCl, that is sodium chloride, potassium chloride, cesium chloride, silver bromide. Okay, it may be noted, this is very important point, it may be noted that AgBr shows, that is silver bromide shows both Frankel as well as Schottky defect. Now see impurity defect. Impurity defect also divided into two parts. Actually, impurity defect is divided into two parts, that is substitutional impurity defect and interstitial impurity defect. Now see, the substitution into impurity defect, actually see the cations. For example, see the host atoms in orderly arrange. Host atoms means, for example, see the brass is the example. For example, brass, see these are the ions of copper, and these are hosts, and takes place of this host by the zinc ion, zinc cation. So this is the example of substitutional impurity defect, for example brass. And next one example, that is interstitial impurity defect, means cations or any kind of cations are comes and situate in the interstitial, that is empty space, situate in empty space. For example, stainless steel is the best example of interstitial impurity defect. So impurity defect is divided into two parts, substitutional impurity defect and interstitial impurity defect. Next one, non-stoichiometric defect. Non-stoichiometric defects are classified into two parts, metal excess defect and metal deficiency defect. Non-stoichiometric means there is not fixed ratio of cations and anions, so they are not in ratio. So this is very important point. There is not fixed in ratio of cations and anions in the solids. They are non-stoichiometric defects. They show non-stoichiometric defects. And further, non-stoichiometric defects is classified into two types, metal excess defect and metal deficiency defect. So first we discuss metal excess defect. Now see, in that metal excess defect, this is due to anionic vacancies. For example, NaCl, KCl. For example, suppose we take NaCl. If the NaCl crystal is heated or decomposed in the atmospheric of sodium vapor lamp, then the sodium atoms are deposited on the surface of crystal, and Cl ions are diffused or released surface of the crystal and combined with sodium atom to give NaCl. And this has happened because of loss of electron from the sodium and form Na plus ions. And there is a release of electrons into the crystal. There is a release of electron. This is very important point. There is a release of electron diffusion into the crystal and occupy anionic sites. Means the electrons are occupied the anionic sites. So that's why this is called as metal excess defect. And because of this, electrons are occupied the anionic sites, and because of this, as a result, there is a excess of sodium, and the anionic sites occupied by unpaired electrons are called as absenters. Means that anionic sites occupied by unpaired electrons are called as what? Absenters. This is very important point. And because of this, that particular solid or crystal imparts yellow color, and this is the very important point, and that's why they impart the yellow color to the crystal of NaCl. Now next point, metal excess defect. This is also another technique. This is also another process. In this process, metal excess defect due to the presence of extra cation at the interstitial sites. For example, say zinc oxide on heating, it gives at room temperature, it gives Zn2 plus half O2 and plus 2 electrons. So these 2 electrons, now there are excess of zinc in the crystal and it forms Zn1 plus X plus oxygen, and the excess Zn2 plus ions move interstitial sites and the electrons to the neighboring interstitial sites. Means Zn2 plus occupies that particular sites, and that's why metal excess defect due to presence of extra cations on the interstitial sites. So Zn2 plus and these 2 electrons also occupy that interstitial sites. Next one, metal deficiency defect. Metal deficiency defect is present in FeO, that is iron oxide, that is not stoichiometric example. For example, see iron oxide, see the typical example type of iron oxide which is a mostly found composition like Fe095 with oxygen, but it is actually range from Fe0.93 to the oxygen or Fe0.96 with the oxygen. In the crystal iron oxide, some Fe2 cations are missing and the loss of positive charge is made up by the presence of required number of Fe3 plus ions. Means there is a changes, Fe2 plus ions are converted into Fe3 plus ions. So there is metal deficiency defect. Now say metal deficiency defects, note that this is very important point. This defect is possible only in compounds of metals that show variable oxidation state. For example, the composition of NiO becomes NiO97, Ni 0.97 with oxygen 1. So this is very important example. FeO and NiO also both shows a metal deficiency defect in both the cases. In first case, Fe2 plus is replaced by Fe3 plus ions, and in second case, in NiO example also same, Ni2 plus is replaced by Ni3 plus cations. So both shows the metal deficiency defect. Now next, see the point defect of crystals. See the diagrams. Vacancy, there is a vacancy. So there is a missing, loss of positive or negative ion. Interstitial, there is a in empty space or interstitial site, there is cation or anion occupied the space. Next, self-interstitial means itself created interstitial site and occupies that or empty space and goes to the empty space or that interstitial sites. Next one, substitutional impurity defect means one atom, one cation is replaced by another cation. That is called as what? Substitution impurity defect. Next one, Frankel defect means leave its original site, cation leave its original site and occupies the interstitial site. Next one, electrical properties of solid. Now already we know there are conductor, insulator and bad conductors of electricity. So that is, bad conductor of electricity means they are bad conductors. Now see the conductors. Crystalline materials that conduct the electricity are called as, already we know, they are conductors. They have energy gap between conduction band and valence band is very low. So there is very low difference. We discuss in next point. Next one, availability of more number of free electrons in the conduction band is the responsible for the electrical conductivity. See, very important. If there is free electrons, then and then there is a conductivity of electricity is possible. Next one, conductivity of conductor decreases as the temperature increases. For example, all metals. Next one, semiconductors. Now see, crystalline materials has conductivity between conductors and insulators are called as semiconductors. These are called as also metalloids. They show the property like conductors or insulators. Okay, so now the energy gap between conduction and valence band is moderate or not like insulator and not, it is a middle or it is a moderate. So there is a availability of few number of free electrons in the conduction band is the responsible for the electrical conductivity. So there is less energy gap. And after semiconductors are divided into two parts, intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor means they are very pure, chemically very pure semiconductors, and they show very poor conductivity or poor conductivity. It has equal number of negative charge carriers, electrons, and positive charge carrier holes. Small current flow by thermal agitations. Say there is a silicon atom. This is the diagram which shows the intrinsic semiconductivity. Now extrinsic semiconductor. Extrinsic semiconductor shows actually two type of semiconductivity, N type of semiconductor and P type of semiconductor. So small amount of impurities added by a process is known as doping, and the number of negative carriers electrons and the positive carriers holes are not equal. Here not equal, and the doping gives negative charge conductor, that is N type of conductivity, or positive charge conductor, that is positive type of conductivity. Now see the N type of semiconductor and P type of semiconductor. N type of semiconductivity is happen when there are group number 15 elements when doped into the group number 14 elements like silicon, then and they show the N type of semiconductivity. If group number 13 elements like boron, when like boron are doped into the family number 14 into the silicon, then they show the P type of semiconductivity, positive type of semiconductivity. There is a lack of electrons, and here in the N type of semiconductivity there is an excess of electrons are present. That's why they are called as negative type of, or that is N type of semiconductivity. Next one, after semiconductors, comparison between intrinsic and extrinsic semiconductors. Intrinsic semiconductors, it is pure form. Extrinsic, it is formed by adding trivalent or pentavalent impurity to a pure semiconductor. Holes and electrons are equal, here not equal. Okay, in P number of free holes are more in p type and number of free electrons are more in n type. Okay, next one, in intrinsic semiconductor, Fermi level lies between valence and conduction band. Here Fermi level lies between valence band in p type and near conduction band in n type, and the ratio majority and minority carriers is unity here, not unity. Next one, extrinsic semiconductor. See from the diagram, donor impurities contributes the free electrons. Okay, donor impurities means, for example, here they give lead. We can take any kind of example. If there is uh, in the 15 type, in the 15 family, if we look the 15 family, then there is a nitrogen family. If we take the nitrogen also here, so here we take the lead example. So from that example we can see that the donor impurity contributes the free electrons. And see the structure, if you see the structure, imagine that this is the n type of semiconductivity, and here see there is acceptor impurity create holes. So family 13, that is boron family, they accept the electrons and create holes, and this is the p type of semiconductivity. Next one, conductors, semiconductors, insulators shown by band theory. See, this is the very important point. See the energy level. Insulators, they show the very large difference between valence band and conduction band. Conductors, there is no energy gap between valence band and conduction band. And semiconductors, there is small energy difference between conduction band and valence band. So semiconductors are also called as metalloids. Already we discussed in previous point. Already we discussed there are two type of semiconductors, intrinsic and extrinsic semiconductor. And also extrinsic semiconductor also divided into two parts, n type semiconductor and p type of semiconductor. Next one, magnetic properties from molecules to solids. See the magnetic property, diamagnetic property, paramagnetic property, ferromagnetic property, antiferromagnetic property, and ferrimagnetic property. So these kind of magnetic properties are shown by solid crystal solids. Now diamagnetic means there are just see, diamagnetic property means they show the paired electrons. So there is no unpaired electrons. All electrons are paired. So there are paired electrons present in diamagnetic. So there is no unpaired electron. So they can't conduct the electricity. So that's why they are diamagnetic. Paramagnetic, there is unpaired electron, but not much, very less unpaired electrons are present. Ferromagnetic, there are so many unpaired electrons are present. Antiferromagnetic, unpaired and paired both are the cancels to each other, so they show the antiferromagnetic. Ferrimagnetic, they show the some upward direction, means some clockwise electrons or some anti-clockwise electrons they show, and that is called as ferrimagnetic. Now see types of magnetism. Look at the chart. Diamagnetic electron pairing. See the electron pairing, no unpaired electrons. In the paramagnetic, at least there is one unpaired electron is present. Now spin alignment with the magnetic field. See the anti-parallel, and here there is a parallel. Reaction with magnets. Here very weakly repel, or they repel. In the diamagnetic, they are repel with magnets, and in the paramagnetic, they are attracted. They are attracted towards magnets. And effect of magnetic field aligns, field bends slightly away from the material, and here field bends towards the material. Now magnetic property of crystal solids. See, diamagnetic repel weakly in the magnetic field, such as solids only paired electrons. See the electrons like this alignment. See the alignment of magnetic field. And the example, that is benzene, NaCl, TiO2, titanium oxide, vanadium oxide. And application, that is in insulator. Next one is paramagnetic. Have unpaired electrons weakly attracted in the magnetic field. They cannot permanently magnetize. For example, O2, VO, vanadium oxide, copper oxide. Next one, application. It is used in electronic devices. Next one, ferromagnetic. Also, they have unpaired electrons, but they have large number of unpaired electrons and attracted in the magnetic field. Such solids can be permanently magnetized. On heating, the temperature called as a Curie point, and these solids change to the paramagnetic solid. See the magnetic alignment, more number of unpaired electrons. For example, iron, nickel, copper, chromium oxide. Applications: chromium oxide used in the audio video taps. And antiferromagnetic. In these solids, changes electrons align themselves in such a way that resultant magnetic moment will be zero. Means one is upward direction, another is downward direction. So cancels the field. One is upward direction, one is downward direction, cancels the field. One is upward, that is clockwise, another is anti-clockwise, so cancels the magnetic field. For example, Cr2O3, chromium oxide, manganese oxide, use instrument of magnetic susceptibility measurements. Next one, ferrimagnetic. Unpaired electrons align themselves in such a way that there is net magnetic moment. See the arrangement of arrows like this and so on. For example, Fe3O4. Thank you.